back to Diksha Karnataka YouTube channel and welcome to Sankalp KCET 2026 series. Here we are discussing all the chapters divided into multiple parts so that you can understand at your own pace, you can learn at your own place, and you also we are doing the previous year questions from the respective chapters as well in KCET. Not only KCET, we are also doing JEE previous year questions. First chapter, all the parts are completed including KCET previous year questions and JEE previous year questions. So if you have not watched it, go to our channel and watch this chapter. Also, it is available in a playlist format, so you can go and check Sankalp Physics playlist and bookmark it if you have not done it. Also, I request you to join our WhatsApp channel. The link of the WhatsApp channel is given in the description. All the class notes, all the updates, everything will be shared through our WhatsApp channel only. So if you have not yet joined our WhatsApp channel, go and join right now. Your account details, your mobile number, etc. will be remain private. It will not be visible to anyone, even not to the admins as well. So you can go and join our WhatsApp channel. And if you have done everything and if you are following our lecture from the beginning, then excuse me, then you can feature in one of these pictures. This is the result of our KCET YouTube channel only. You can see the result. The students who have studied from us throughout the year, they have achieved excellent result along with them as well, and your picture can be here in the next year. So if you want to feature in our exclusive segment, then you have to study hard right now. Little bit difficult for you, I know. Your colleges are started, but many of you are asking, sir, start. So we have started, but unfortunately I am not seeing too many of you are commenting or watching our videos. I know the views will go up when your exam is coming, but till then it might be too late. So don't wait for that, start studying right now. Okay, so let me explain the chapter once more. I have already explained this. So electric potential, equipotential surface, potential energy and potential point charge, electric potential due to a point charge, system of charges. Then we have equipotential surface, relationship between electric field and voltage, potential energy due to a system of charge, potential energy due to a dipole. These are all covered in our last lecture. So if you have missed that, go and check that out as well. Today I am going to discuss about conductors and dielectrics. In that part, conductors and dielectrics will be discussed separately, and in the dielectric portion we also discuss about polarization. In last part, next part, we will be discussing capacitor, everything related to capacitor, the parallel plate capacitor, combination of capacitors, energy stored in a capacitor. So everything related to capacitor we will be discussing our part 3. So if you are wondering about that, you can check that out once that video is out. Now let's continue with today's lecture. So first is electrostatics of conductors. There are few important points you have to remember. Based on that, you might see some MCQ questions not only in KCET but also in your board exam. So board exam marks are important for KCET, so that's why we are trying to balance both. So metallic conductors contains mobile charge carriers, namely electrons. Mobile means not your mobile phone that you used to call. Mobile means which can move, right? Metallic conductor contains a lot of charges that can move, right? And those charges are called electrons. Is in a metal, the outer or valence electrons, you are familiar with the term valency, you have studied in your chemistry class. So in a metal, the outermost electrons take part away from their atoms and are free to move. So the electrons which are in the valence orbit, they can come out of the come out of the atom, and they can carry the current, carry the electricity, which is very, very essential for us. In the next chapter also we will discuss more about it. These electrons are free within the metal. That means, so they are part of the atom they are no longer part of the atom, they are free now, but still they cannot escape the metal. They are moving, they can move only within the metal. That is very, very essential. They cannot come out of the metal by their own free will, but they are still available, they are still free, but they are still bound to the atom, bound to the metal. Okay, and not free to leave the metal. So as I said, they are still bound, but partially free. They are partially free, like you, when you study at home, you say, if I study for 2 hours, will you allow me to watch a movie, or will you allow me to watch my favorite TV series, web series? So your parent says, yes, if you study for 2-3 hours, I will allow you to watch your favorite TV series. So when you are studying, that means you are free for that 1 hour after your study is completed, but still you are not allowed to leave, go anywhere else. You are sitting in your home only, but you are watching your favorite series, or you are playing your favorite games along with your friends, right? So it is like that kind of scenario. The free electrons form a kind of gas. So the free electrons, they are like a gas. It is called electron gas. They collide with each other and with the ions and move randomly in different directions. So when they are free inside the metal, they behave like a gas. Gas, we know that kinetic theory of gas chapter last year we have studied it, that gases particles are moving randomly, they are colliding with each other, and that collision is very similar to that of gas, right? And the motion is random motion, and their collisions are also random. Okay, so in an external electric field, they drift against the direction of the field. This is the next chapter. This is the concept of the next chapter. But you should know that when you apply an external electric field, these electrons, they are no longer random. They slowly move towards a particular direction. That motion is called drift motion. That happens only when there is an electric field is present. Okay, so in the presence of electric field, electrons drift. Very, very important concept. Now a few more points. Inside a conductor, electrostatic field is 0. So if you consider a conductor, inside a conductor, electrostatic field is 0. No electric field line can pass through a metal. So that's why electric field is 0. So if you can see that in a presence of external electric field in a conductor, what happens? This is the electric field which is there by the external agency E naught. Okay, E naught is the external electric field. So if you apply an external electric field, in response to that external electric field, the conductor will develop an internal electric field. Because of this, charges will separate. Okay, there will be an internal electric field. The internal electric field will be exactly equal to that of the external electric field. So inside the conductor, electric field will be 0. So inside the conductor, electric field will be 0. Very, very important. In the presence of external electric field, in a neutral conductor, it will there is no electric field inside a conductor. At the surface of a charged conductor, the electrostatic field must be normal to the surface at every point. So what is the meaning of that? So suppose we have a conductor, we generally prefer spherical conductor. So at any point, if you consider the electric field will be normal to the surface. Electric field will be normal to the surface. Okay, a surface is basically the tangential surface. So if you draw a tangent at any point, electric field will be normal to the surface at each and every point. This is not only about these 2 points. You take any point, and electric field will always be normal to the surface. The interior of a conductor can have no excess charge in the static situation. So in the static situation, when no current is flowing through the conductor, the metal cannot have any extra charge. That means it cannot have any positive, extra positive charge, or any extra positive, negative charge inside the conductor. Very, very important. Even if it is a charged conductor, okay, it will not have any charge inside the surface. Okay, so even if there is a charge inside the surface, so equal number of positive and negative has to be there. Excess charge means extra. So suppose I have 10 coulomb positive, 11 coulomb negative charge, then that minus 1 coulomb, which is excess charge, that cannot stay inside the conductor. Very important point, the extra charge will be staying outside the conductor, on the surface of the conductor. Okay, so the excess charge must reside at the surface. The electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. So suppose I have a conductor. Okay, so the potential inside is constant. Electric field is 0, but potential is constant. Potential is constant, and that constant is exactly whatever is at the surface. Okay, so surface will also have the same potential. Surface will also have the same potential. Electric field at the surface of a charged conductor is given by E is equal to sigma by epsilon naught n cap. This is for a charged conductor, not a charge sheet. In case of charge sheet, it is 2 epsilon naught. Okay, for a conductor, it is sigma by epsilon naught. Very, very important point to remember. For a charged sheet, it is sigma by 2 epsilon naught. For a charged conductor, it is sigma by epsilon naught. So it is twice the electric field on a sheet. Right, so sometimes students get confused. There was one question also in the last year where the question was based on this fact that electric field on the surface of a conductor is sigma by 2 epsilon naught. Is actually wrong. On the surface of a charged conductor, it is sigma by epsilon naught, not 2 epsilon naught. Okay, now electrostatic shielding, it is a very unique property of a conductor. Electric field inside a cavity in a conductor is 0. Whatever be the size and shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be kept. So if you have a cavity, cavity means what? Cavity means hollow space. Cavity means hollow space. So for example, if you play cricket using tennis ball, right, we all have played using tennis ball. So once the tennis ball is broken, once the parts are coming out, you see that inside of the tennis ball is hollow, right? Only the rubber portion is outside and inside part is hollow, right? So in that case, that hollow portion is called a cavity. Okay, cavity means, suppose this is a conductor or your table tennis ball, not table tennis ball, tennis ball. Okay, this is the thick outer layer. Okay, this is called cavity. Right, cavity also happens in one of the places, you know, right, inside our teeth. There was a lot of advertisement happening that if you use this toothpaste, your cavity will be gone. Cavity, right? So cavity means hollow space. Okay, and the important part about conductor is that if you keep something inside, okay, if you keep anything inside, the electric field will be 0 inside it. Okay, potential will be constant and electric field will be 0. So even if you are experiencing any external electric field, even if this system is charged, does not matter, the electric field inside will always be 0. That's why it is safer for you to stay inside a car when there is an electric storm or lightning storm is happening outside. Okay, because the car, if it is made up of metal, right, mostly there are some windows etc, but mostly it is connected, considered to be a metal box. So if something happens, some electric lightning strikes the car, you will be safe inside because of the electrostatic shielding. Okay, there was one question that an aeroplane was flying and why it is safe when electric lightning strikes the plane, because it's a metal. Okay, whatever is happening, it will happen on the surface, nothing can penetrate, nothing can go in, so you will be safe inside the plane. So this is very, very important point to remember. Okay, also the costly equipments Okay, so there are some sensitive equipments which can show deflections in the presence of external electric field. They are kept in a metallic box. Okay, they are generally kept in a metallic box with windows of glasses so that you can observe it, but overall it is kept in a metallic box so that total electric field inside the equipment can be zero. In some cases the entire room is made up of metal so that no external interference can happen in that equipment. So that is also very, very important point to remember. Now let's move into dielectrics. Okay, dielectrics are non-conducting substances. So first of all, so far whatever we have discussed, it is about conductors. Conductors conduct and they have certain properties as well. They have free electrons, and if you apply electric field, the electrons will drift. That means they can conduct electricity. Whereas dielectrics, which are very, very important part of our journey, especially this chapter, that dielectrics are non-conducting substances. So far the same thing are called insulators as well, and we have ignored it, right? Mostly we have ignored insulators because our most of the time our focus was on conductors and later on some of the semiconductors as well. But insulators or dielectrics, they are also very, very important. They also play a major role. We will see that, but they are also very, very important. In contrast to conductors, they have no or negligible number of charge carriers. So by nature they do not have any free electrons. That is the meaning of it. Okay, negligible charge carriers are electrons, so they do not have any significant number of electrons. Number of electrons is very, very less. Okay, it turns out that the external electric field induces dipole moment by stretching or reorienting the molecules. So when you apply an external electric field to these substances, okay, the molecules themselves, now here we are talking about molecules. So molecules, basically insulators have more than one atom attached to a molecule, right? For example, say HCl, okay, or H2O. H2O is a polar molecule. So they are having, but they are insulator by nature, or they are dielectric. So you can consider them to be dielectric. Even air is a dielectric. So by nature they have more than one atoms attached to it. Okay, it turns out that the external field induces a dipole moment. So when you apply external electric field, okay, it induces means as long as the field is present, the dipole moment is present. If the dipole electric field is gone, the induction is gone. Okay, by stretching or reorienting. So reorienting means obviously a molecule will have a positive core and some electrons, so they will try to align these positive and negative so that they develop a dipole moment. Okay, the collective effect of all the molecular dipole moments is the net charges on the surface of the dielectric, which produce a field that opposes the external field. Similar to that of conductors, there will be also a internal electric field that will oppose the external electric field. So by nature, this is the nature of not only for you or me. Whenever suppose I am teaching you, I am trying to tell you that go and study, there is an internal field within you that says that don't study, we still have a lot of time. Okay, so that inertia or that property which tries to resist whatever is going on, that is also present in case of dielectrics as well, and they also try to prevent the external electric field. Okay, the opposing field is so induced, it does not exactly cancel the external field, it only reduces it. In case of conductor, it was completely cancelled. External electric field, internal electric field, exactly opposite, completely cancelled. But in case of dielectric, it cannot be cancelled completely, but it can be reduced. So the effect of the external electric field can be reduced. So let's see over here. Here we have a dielectric. Here we have a conductor, and here we have a dielectric. In case of conductor, as you have seen that internal electric field and external electric field, they are exactly equal, and the net result was 0. In case of dielectric, what happens is that this is the external electric field and there is a internal electric field. The internal electric field is smaller. Internal electric field is smaller compared to the external electric field. So the internal electric field is smaller compared to the external electric field. So the combination of E naught plus E in are not zero. See, this is not zero. That means there are some resultant electric field present in this direction. So there is a net electric field in this direction. Okay, so net electric field is present. In case of conductor, net electric field is zero. Now dielectric constant or relative permittivity, this is also very important concept. So dielectric constant represented by capital K, very important because sometimes students confuse it with Coulomb's constant. Coulomb's constant is generally written by small k. Okay, the Coulomb constant is written by small k, dielectric constant is written by capital K. Okay, so this is 1 by 4 pi epsilon naught, Coulomb constant. This is dielectric constant. Okay, dielectric constant generally represented by capital K, and sometimes it is also called relative permittivity. Relative permittivity is represented by epsilon r, and it's defined as the permittivity of the medium divided by permittivity of the free space. Permittivity of the free space is epsilon naught. The value is known, 8.85 into 10 to the power of minus 12. So dielectric constant for a particular medium, permittivity of the particular medium, if you know that, you can calculate it. This is the smallest value, epsilon naught. So epsilon will always be greater than epsilon naught. So dielectric constant will always be greater than 1. Very important. For free space, that is vacuum, or for air, dielectric constant is 1. Okay, because air, we assume that air almost has same value as epsilon naught. So for air, dielectric constant is 1. Other than that, for any other material, dielectric constant is always greater than 1. Dielectric constant less than 1 is not possible. Very important point to note. There is one question that I have seen in one of the board paper, not board paper, I think a pre-board paper in one of the districts. This question came: dielectric constant of a metal. Dielectric constant of a metal. Most people answered it 0. Remember that dielectric constant less than 1 is not possible. It has to be infinity. Okay, either 0 or infinity, but out of that it has to be infinity. Now remember that inside a metal, permittivity of the medium is infinity because it's a perfect conductor, so permittivity is infinite, so its dielectric constant is also infinite. Very important point to remember. Okay, it is not constant, it is not 100, because metals are considered to be good conductors, so in that case it will be infinity. Dielectric constant will be infinity. Just remember this point. Based on that, you might see some objective question in your board, not in KCET but in your board exam. Now let's see one more question. Two charged spheres separated at a distance d exert force F on each other. If they are immersed in a liquid of dielectric constant K, then what is the force? Very interesting question. So this question is actually related to Coulomb's law, but let us understand. I will do it in detail so that in future maybe you will be able to answer some questions related to that. So two charged spheres, suppose the charges are Q1, Q2, they are separated by some distance, say R. Okay, so initially what is the force between them? Initially the force between them is 1 by 4 pi. I am, just to avoid confusion, I am writing 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught Q1 Q2 by R square. So this is the force. Now if you take this entire system and immerse it into the medium of dielectric constant K, you take this and you put this entire system into a dielectric medium of radius, same distance, everything remains same. Okay, only the dielectric constant is K. Now what will happen? See, the Coulomb's law will remain same. The expression remains same. Only thing that will change, F dash, I am saying this force is F dash, it will be 1 by 4 pi epsilon Q1 Q2 by R. So this medium has a permittivity epsilon. So only thing that will change is this. Okay, so epsilon will become epsilon naught will become epsilon. Now we have to find a small relation between K and epsilon. Okay, so we know that dielectric constant is given by epsilon naught, right? So what is the value of epsilon? So epsilon can be written as K into epsilon naught, right? Cross multiplication. So put this value over here. So we will get 1 by 4 pi epsilon naught into K. So there is a square also, sorry. Q1 Q2 by R square. Okay, so now what? So if you see this one and this one almost same except for this dielectric constant K factor. So what we have to do, we have to adjust it. How can we adjust that? We have to, so this entire thing is the force. Okay, so the entire thing is the force. So we can write this as F by K. Okay, so the new force will be F by K. So this will be the correct answer. This will be the correct answer. So force will be K times less. So if you take the system and if you put it in a dielectric medium, the force will decrease and it will be decreased 1 by K times. Clear? Now if you have any doubts, if you want to choose a better college, then definitely Diksha has a lot of offline campuses as well. You can join one of them. You can fill the link given below. You can fill the form and our representatives will contact you if you are not satisfied with your current college, or suppose you want to recommend Diksha colleges to one of your relatives who might be studying in class 10th, or those who are currently studying in class 11th and later on they want to switch to class 12th to a better college, then definitely you can fill that form as well and our representative will contact you and you can see the wonderful result achieved by all the Dikshites who have studied in our Diksha campuses across all over Karnataka. Now let's move on. Dielectrics we are studying about, they can be classified into two parts. First is non-polar dielectric and second is polar dielectric. So these are the two categories on which they can be separated. Let's see one by one about them. What is the special about non-polar and polar? So first we will discuss about non-polar dielectric. A non-polar molecule, the centers of positive and negative charges coincide. Okay, the molecules then has no permanent or intrinsic dipole moment. So individually one molecule, this is happening in the molecular level. Okay, so positive and negative centers, they coincide. So for example, suppose we have a positively charged nucleus and electrons are orbiting. Okay, if the electrons are orbiting such a way, if it is perfectly circular path, then the center of this positive and this negative will coincide, and we will denote such molecule like this. Okay, it is very difficult to denote like this, so you will denote it like this, because not every time it is possible for you to draw the entire molecules, right? It will be very big. So basically this represents a non-polar molecule. Okay, non-polar molecule, centers of positive and negative, they are coinciding, they are staying together. Okay, and example given here is hydrogen, which because of their symmetry have no dipole moment. Okay, so they generally do not have any dipole moment. The dipole moment, internal dipole moment is 0. So for a non-polar molecule, the dipole moment for a non-polar molecule is 0. Intrinsic. Extrinsic we will see in a while. Okay, a polar molecule is one which the centers of positive and negative charges are separated even when there is no external field. So even if there is no external field, molecular level, the center of positive and negative, they are separated. For example, in hydrogen OH bond, suppose they have given H2O, I am just talking about OH bond, right? We all know OH bond, okay, it has some charge itself. But what happens in this bond? Let's see. So they are sharing a electron pair, right? Hydrogen is giving one electron, oxygen is giving one electron, and they are sharing it. But while sharing, oxygen is basically is the boss of the room. He says, okay, hydrogen, you are weaker, so even if we are sharing, I will have keep the electrons near me. Okay, I will keep the electrons near me. It has a very high electron affinity, so it will take those two electrons near it, and that's how it develops a dipole moment. So you can say that this becomes delta minus, this becomes delta plus, right? We have all done this in chemistry, right? So this is how it develops a dipole moment, and that is why they have a permanent dipole moment. Okay. An ionic molecule such as HCl or a molecule of hydrogen are examples of polar molecules. Now there is a note in polar crystal. So this is about only one molecule. Only one molecule. Crystal means where multiple molecules are present. Crystal means multiple molecules are present. For example, ice or a glass of water. Okay, even though glass of water is not a crystal, it is still when you are considering bulk material basically. Okay, in a polar crystal, the net dipole moment is 0. The net dipole moment will still be 0. This is because the molecular dipoles are randomly arranged. So we will see that in a while. The molecular dipoles are randomly arranged so that their net dipole moment is 0. So even if the molecules, individual molecules, have some dipole moment, so the net dipole moment is not 0, net dipole moment is not 0, but still in case of bulk material, bulk of the polar molecule, the net dipole moment is still 0. The net dipole moment is still 0. P net is still 0. Okay, so then there will be some confusion among the students based specifically in case of MCQ questions. The net dipole moment of non-polar molecule is 0, net dipole moment of polar molecule is not 0. So the student will say, okay, non-polar molecule, polar molecule, the net dipole moment must not be 0. Molecular dipole moment is not 0. Okay, molecular dipole moment is not 0. Net dipole moment is still 0. Okay, clear? Now let's see the dielectrics in external electric field. Now we are applying some external electric field. This is non-polar, this is polar. Okay, so as I said, non-polar molecules are represented using this symbol, plus and minus keeping together. So in this case, net dipole moment is 0, individual molecular dipole moment is also 0. Both are 0. Okay, now when you apply some external electric field, okay, so when you apply some external electric field, the electrons move away from the electric field. Suppose you have applied an electric field in this direction. Okay, now in the presence of external electric field, what happens? We know that positive charges move towards the electric field, negative charges move away from the electric field. So the molecules, even though they were initially they have no dipole moment, in fact after applying external electric field they develop a dipole moment, and in doing so they also develop a internal electric field. Okay, so internal electric field is developed in case of non-polar molecules as well, non-polar dielectrics as well. Okay, now in case of polar molecules, as you can see that positive and negative, they were separated, but still they are randomly oriented, so the net dipole moment was still 0, net electric field was still 0, internal electric field was still 0. Now when we apply some external electric field, the dipoles will be oriented, dipoles will get oriented according the same way. Okay, positives will slowly move towards the electric field, negatives will move in the opposite direction of electric field, and they also will develop some internal electric field. So this is E naught, this is E internal. So they will also develop an internal electric field, obviously in the opposite direction of the applied electric field. And again, in both cases, okay, there is no such difference. Only difference is that in this case, centers of positive and negative, they are getting separated. In this case, the positive and negative, they are getting reoriented. Here separation happens, here reorientation happens. Otherwise, in terms of electric field, there is no such difference, but how it is achieved, there is a difference. Okay, because it was initially 0, so now their centers, the positive and negative are getting separated, so the molecule is getting stretched. So if you remember, there was one question, the centers are getting stretched, so this is one of the cases, and in this case they are getting oriented. Okay, they are getting reoriented. So this is reorientation, this is stretching. Now let's see one question. Which of the following correctly describes the behavior of a polar and non-polar dielectrics in an external electric field? So this is a question that I was talking about. I think this question came in one of the exam, I don't remember which year it was, but it is a very common question. Both polar and non-polar dielectrics have permanent dipole moments. So both polar and non-polar dielectrics do not have permanent dipole moments. Obviously, molecular way, polar has dipole moment, but non-polar does not have. So first statement is incorrect. So first statement is incorrect. Polar dielectrics align their dipole moments with the external field, while in case of non-polar dielectrics, a dipole moment is induced in response to the field. Okay, so polar dielectrics align their dipole moments, so they already have dipole moment which is getting aligned, and in this case, in non-polar, it is getting induced, right? So this statement appears to be correct. So let's see the other two statements. Non-polar dielectrics align their permanent dipole moment. So as you see, non-polar dielectrics does not have a permanent dipole moment, so this statement is incorrect. Now let's see the last statement. Polar and non-polar dielectrics behave identically in the presence of an electric field, showing no difference in polarization. So as I said, they are even though they are behaving similarly, but they are not identical. Okay, identical means everything has to be same, but they are not identical. In case of polar dielectric, they are getting reoriented, whereas in case of non-polar dielectrics, they are getting stretched. So you can say that dipole moment is induced in it. So this statement is also incorrect. So option B is correct statement. So this kind of deep thought questions might come in your KCET exam as well. So you have to be prepared for that as well. And not even KCET, this question can come in your board exam as well. Okay, now let's discuss about polarization. It is also very important concept. When a polar or non-polar, very important, polar or non-polar, both, okay, a dielectric develops a net dipole moment in the presence of an external field. So as we know that when the external field is not there, the net electric field, net dipole moment is 0, right? If you do not have any net external electric field, the net dipole moment is 0. It only develops when you apply an external electric field. So that is very important. So they develops a net dipole moment in the presence of external electric field. The dipole moment per unit volume, dipole moment per unit volume is called polarization, and it is denoted by capital P. For a linear isotropic dielectric, it is given by polarization equals to epsilon naught chi E vector. Okay, so we will see some questions based on this formula as well in future, but right now just keep it to here. Here chi, this is called chi. Okay, this is like a x, but x has one arm curved like this. Okay, so this is like this, and this is the another arm of the x. So this is called chi. Okay, chi, but it is pronounced as chi. Okay, so chi e is a constant characteristics of the dielectric and is known as the electric susceptibility. So very, very important term, electric susceptibility. We mostly deal about magnetic susceptibility, but even in electricity also there is a possibility of electric susceptibility. So how it can resist, basically susceptibility means how susceptible it is. So if I tell you, Arek, please come and play PUBG with me. So basically if you are susceptible, then you will say, come, let's go play, right? But if you are stronger enough, no, I will not play, I will not go, I have to study. So that means you are not highly susceptible. Your susceptibility is very high, not low. If your susceptibility is low, then you will get distracted very quickly. So those who are watching this video till this moment, please mention that in the comment below, so then I will know that you have a very high susceptibility, you are doing great job and you will achieve great things in future. Okay, now what happens in the polarization? As you see that in case of external electric field, a dielectric medium gets polarized. Okay, so this is the polarization, and there is a surface charge density on this side, there is a negative surface charge density in the opposite side of the electric field. The polarized dielectric is equivalent to two charged surfaces. So basically you can say a polarized dielectric, this is a polarized dielectric. Okay, it is equivalent to two charged surfaces. One surface has a surface charge density here, sigma p positive, not positive, sigma p is itself is positive, and another is minus sigma p. If this is sigma p, this has to be minus sigma p, because net charge has to remain 0. Okay, with induced surface charge densities, say sigma p and minus sigma p, the field produced by these surface charges opposes the external field. So as I said, this internal electric field will oppose the external electric field because it acts in the opposite direction. Electric field always points from positive to negative. The total field in the dielectric is thereby reduced from the case where no dielectric is present. So in case no dielectric is present, suppose only air is present or vacuum is present, then whatever electric field will be, if you apply a small amount of dielectric, the electric field will reduced by some value. Okay, we should note that the surface charge density plus minus sigma p arises from the bound charge and not free charge. What is the meaning of bound charge? So if you remember in the example of conductors, I said that electrons are out of their valence bond. Okay, they can come out of their valence bond and they can roam freely inside the metal. So those are called free electrons, not the bound electrons. But if the electrons are bound even to their protons, if electrons are bound to their protons, that means electrons cannot leave the valence orbit. Even if they are in valence orbit, they have to stay in the valence orbit itself. So they cannot come out of the valence orbit like it had done in case of metals. So that's why it is called bound charges. Free charges means if they can come out of the valence orbit, they are called free electrons. Okay, so it occurs due to bound charges and not free charges in the dielectric. So that is the difference between dielectric and conductors. Now here are the homework questions. Please see these questions. Okay, these are very, very important questions, and if you want to download this lecture PDF, please join our WhatsApp channel. You will get this question paper, you will get the entire class notes along with all my handwritten annotations, right? So just join the WhatsApp channel. The link of this is given in the description. Next question. Polarization, this is easy question. Okay, first question was slightly tricky and this question is slightly difficult. Last question I think came in Comet K. So check these two questions, try to answer it and let me know in the comment below what is the answer. WhatsApp channel description is given in the description. Also, if you have not yet subscribed to our channel, don't forget to subscribe to our channel to get all the KCET related information, counseling information, class lectures, notes, PDFs, etc. So I'll be back with the part 3 of this lecture. Till then, bye.